Hi everyone, thanks for tuning in or being here in the room. And I just want to start by thanking Anthony and Geordie and Anna and Hannah for the wonderful opportunity to visit MSRI for a couple of weeks. SMRI, SMRI. Murray and I are having a great time, and not so long ago I went to see a Taylor Swift concert, and Charlie XCX was the warm-up act. So I am Charlie XCX and Murray is Taylor Swift for the purposes of today. So what I want to talk about is some stubborn conjectures concerning rewriting systems, geodesic normal forms, and geodetic graphs. I'm going to tell you what all these things mean and try to convince you that they're interesting and related, and that stubborn questions are worth spending a bit of time with. Okay, so we'll start with some background on directed Cayley graphs. So the sort of objects we care about are groups, but we often picture groups with Cayley graphs, and there's just, for the sort of work we're talking about here, there's a little confusion I need to clear up before it gets in the way. And so if we have a finitely generated group G, and sigma is a finite monoid generating set for G. So what does that mean? It means every element of the group can be written as a product of elements in sigma. Now that's a little different from often we say can be written as a product of the elements in sigma or their inverses. And so here we really don't want to include inverses if they're not in sigma. So then we have a directed Cayley graph, which is a directed graph where you have a vertex for each element of the group, of course, and you have a directed edge when you have from G to GX if X is in sigma. And then for each vertex of the group, G0, there's a one-to-one correspondence between words that you can make with your monoid generators and directed paths in your directed Cayley graph that started at G0. And the shortest directed path between two vertices is a geodesic. Geodesics are good. They're the shortest ways to get between vertices in the Cayley graph, which means that they correspond to the shortest way to spell the corresponding group element using your generators. So when we're working in algebraic structures like groups, we have generators. We need to construct group elements as product of generators. It's great if you can use the shortest product possible. And so that corresponds to the shortest path in the directed Cayley graph. So in the special case that that your alphabet is closed under inverses, that means every element of your alphabet has an inverse which is in the alphabet. Then directed edges in these graphs come in pairs. That's great. So you may as well think about an undirected Cayley graph. So you don't have to think about a directed graph. What's the real difference between directed graphs and undirected graphs? Is in directed graphs, you may not be able to go in both directions across an edge, whereas in an undirected graph, you can do that. So here's where things get a little confusing. So if we can use an undirected Cayley graph, then we're just going to collapse our two directed edges into an undirected edge. But we still tend to draw a directed graph, because if we want to understand how paths correspond to spelling group elements using the generators, then we still need to know which direction corresponds to traveling in the positive G direction and which direction, or positive X, and which direction corresponds to going in the direction X inverse. So I think it'll help to see some wonderful examples here. Scribbled in my hand. And perhaps this will show you why I felt I should talk about it to start with. I've got the same group here. It's the cyclic group of order 4, and I've drawn 4 pictures, 2 directed Cayley graphs and 2 undirected Cayley graphs. And you might notice that some of them look the same. So in the top left-hand corner, we have a directed Cayley graph for this group, where the only generator we have is 1. So the group elements are 0, 1, 2, and 3, and we have generator 1. So red arrows correspond to 1. And maybe if you have a look at that graph, you'll notice that there's a unique shortest path, directed path between any two vertices. So that's neat. If you want to move from one place to another, there's a unique best way to do it. Of course, there are other ways. You could go around the circle many times and come back to where you want to go, but there's a unique shortest path. And then in the next graph, in the top right-hand corner, we've got the same group, but now I've got 1 and 3 as my monoid generating set. And now there's two different shortest paths to get between 0 and 2. You could do 1, 1, or you could do 3, 3, and that'll get you to the same place. So it doesn't have unique best ways to do things. Now, in the bottom left-hand corner, we have an undirected Cayley graph because 1 and 3 are inverses here. So my generating set is closed under inverses. So I really have my directed Cayley graph edges always come in pairs. So I could just think of it as an undirected graph, but I still have to label some directions so I know how paths correspond to words in the generators. So the picture I draw is exactly the same as the picture I draw in the top left-hand corner, but it means something different. In the bottom left-hand corner, you're allowed to go backwards along an edge. But in the top left-hand corner, you're not allowed to go backwards along an edge. And that's because my generating set has inverses in the bottom left-hand corner. And then just to mix it up, on the bottom right-hand corner, we have the same group, and now I have all of the non-trivial elements are generators. So that means that this generating set is closed under inverses, so I can draw the undirected Cayley. So there is such a thing as the undirected Cayley graph. That makes sense to me, but I'm still going to draw a directed Cayley graph. So I only need to draw edges for 1 and 2 because 3 is the inverse of 1. And what you might notice here is that this graph in the bottom right-hand corner also has unique shortest paths between vertices. So this is a trick that you can pull with any finite group you like. If you have a finite group, you can construct an undirected Cayley graph for your finite group with unique shortest paths between vertices just by using every non-trivial element as a generator. Because then you can always get from one vertex to another by crossing one edge and you're fine. So this is a trick that will come in handy for us. But does anyone have any questions about the setup here and directed and undirected? Okay. So, all right. So here is a really poor attempt at a free group of rank 2. And I apologize. I thought I was going to do much better than this and I didn't. And then I ran out of time to improve it. But I've got the generators. It's a bit hard to see because of the zoom thing here, but the generators are A, B, A inverse, and B inverse. And of course, one of the things you might notice here, there's an undirected graph really, but I'll draw a directed graph to give the orientation of the paths. And there's unique shortest paths between things because it's a tree. So that's good. Oh, there we go. Get it like that. Okay. So here are the 3 important classes of groups that I want to talk about today. And they're nested. There's a proper containment here. The first is we're going to think about finitely generated groups. So we're going to say that a group G is a hyperbolic group if for some and hence every, it's not obvious, but it can be shown, for some finite generating set, which is closed under inverses, triangles in the undirected Cayley graph are thin, whatever that means. What does it mean? So if you think about equilateral triangles in the Euclidean plane, and you think about the distance between the midpoints of sides, you realize that there's no bound on, there's no universal bound on this distance. In other words, if someone gives you a big number, you can make an equilateral triangle with the property that the midpoints of sides are further apart than the big number you're thinking of. That's not what happens in hyperbolic geometry. Triangles are thin. No matter how, there's some universal bound on the distances between midpoints of sides in triangles. It's quite remarkable, and it's sort of a distinguishing feature of hyperbolic geometry from Euclidean geometry. And a rather remarkable thing is that this distinction is very effective at identifying a class of groups called the hyperbolic groups, which behave differently from other groups. It's a really beautiful observation that one can apply that the sort of characterization of the behavior of triangles to Cayley graphs of groups, and it identifies some groups as behaving differently from others with profound consequences for those groups. So hyperbolic groups are the ones whose Cayley graphs have thin triangles. What about virtually free groups? There's a more sensible definition of virtually free groups if you want to get started, if you want to understand what the word virtually free means. Virtually free, my definition here is that a group is virtually free if, when we look at its undirected Cayley graph, the result is the undirected Cayley graph looks like a tree. So it's what they call quasi-isometric to a tree. And one common way of saying that is if the Cayley graph were to recede into the distance, eventually you couldn't tell the difference between what you're looking at and a tree in that. So it's not, the Cayley graph doesn't have to be a tree, but it's quasi-isometric to a tree. And for the record, the phrase virtually free, another way of saying it is that there's a finite index subgroup, which is a free group. So we've got these two types of groups, hyperbolic groups and virtually free groups. And I've given you definitions in terms of the geometry of their Cayley graphs. And every virtually free group is hyperbolic, but there are hyperbolic groups that aren't virtually free, so there's a proper containment there. And then there's this, and they're kind of awesome names, hyperbolic and virtually free. And then we have the next class of groups, which are called plane, which is like terrible advertising for a class of groups. The other name for them is basic. And people may as well call them boring, but they're not boring as far as I can see. They're sort of, I'm going to maybe try to convince you that they're not boring, but what are plane groups? Well, plane groups, we don't have a definition of them to give in terms of their Cayley graphs, but I can tell you that a plane group is one that's isomorphic to a free product of finite groups and infinite cyclic groups. Maybe I'll move this again. Ah, there it is. Oh. Dock to the top. There we go. Okay. So the plane groups are virtually free, but there are virtually free groups that are not plane. Okay, so Pascal's function on groups. Mike Shapiro worked in Australia for a long time, and now he's living in America and has been for a long time. He was in Melbourne in the 90s. Right, yep. So Mike Shapiro is a real character, a lot of fun to spend time with. Really insightful mathematician, and he wrote a paper in 1997 where he it starts off in a really fun way. He defines a function. He wanted to think about how many different geodesics there are between group elements. And he defined a function which he called the Pascal's function on a group with a finite monoid generating set. And the Pascal's function is, for each group element, G, this function takes as input a group element and gives as output how many geodesics there are from the identity element to your element G. Another way of saying it, how many shortest ways to spell that group element are there in your generating set? So why is it called Pascal's function? Well, the name is inspired by what we see in the first quadrant. When you look at the direct product of an infinite cyclic group with itself, you've got and with the most obvious generating set, the most natural generating set, if you start to count how many geodesics there are from the identity to various points, you start to see Pascal's triangle in the first quadrant. So Mike thought this was kind of cool, and then he went on to do more than this, but that's why it's called Pascal's function. All right, so we can start to think about what Pascal's function might be like in other groups. And of course, it depends on your generating set, because if you mess with a generating set, you create new ideas of shortest paths, and you change the behavior of how many geodesics there would be. And so you change Pascal's function for your group. So if you've got a free group, then with the right generating set, see if I can move this again. Then the Cayley graph, undirected Cayley graph is a tree, so they're your unique geodesics between vertices. So the Pascal's function is identically one. Of course, one of the charming things about that is that every time you think of it, you want to have a group element in mind, there is a unique best way to write that group element. The best because it's the shortest. It's the one that makes sense. And of course, we get ourselves into trouble in mathematics all the time if we don't understand when we're looking at the same thing written in two different ways, right? We have to put an effort all the time to take whatever algebraic structures we're looking at and understand, okay, how can I tell when I'm looking at two strings of generators whether they actually are telling me about the same group element? We know that's a highly non-trivial problem, but here we have a favorite way to write each group element, and that's really powerful. So an obvious choice for normal forms. All right, here's a virtually free group. So here's a group that has, as a finite index subgroup, a free group. Of course, that finite index subgroup that's free is just the infinite cyclic group. So if you take Z direct product with a group of order 2, and with the most obvious generating set, 1, 0, and -1, 0, and 0, 1, then the Cayley graph is this ladder construction, and we can figure out Pascal's function for this. If you're moving to another point from the identity to another point on the bottom of the ladder, there's a unique best way to do it. But if you're moving to a point on the top of the ladder, you get to make a choice about when you make that move from the bottom to the top. And so I guess I could have written that as the absolute value of A choices. All right, well, here's a plane group. Wonderful, really great. All right, with the right generating set. So PSL to Z is actually isomorphic to a free product of two finite groups, which makes it a plane group. Remember, the definition of a plane group was free products of finite groups and infinite cyclic groups. So this is a plane group. And maybe you'll see why plane groups are virtually free groups just from this one example. You get the idea of it, that you can see that the Cayley graph, as we're starting to draw it here, looks a lot like a tree. It's quasi-isometric to a tree. If this thing were to recede into the background and those blue triangles became blue dots, you would start to see this looks more and more like a tree. Okay, so Pascal's function here is identically 1. This has unique geodesics between vertices. Wherever you want to go, there's a unique best way to go. And that's really nice. Of course, it comes from the free product structure and from the fact that we have found a way to represent the finite factors so that as you move within the a blue triangle in the red, there's a unique best way to move there. And then we've got this free product structure. So maybe you can see from here that I mentioned earlier, if you have any finite group, you could just use every non-trivial element, non-identity element of your finite group as a generator, and your Cayley graph for your finite group will be a complete graph. It'll have unique geodesics. So if you have a plane group, which is a free product of finite groups and infinite cyclic groups, you can just combine these geodesic parts in a way that gives you a Cayley graph of your plane group, which is geodesic. Well, geodetic is the word I should use for a graph in which there are always unique geodesics between vertices. All right, so here's what Mike Shapiro did in his paper, besides observe that he could see Pascal's function, and that was kind of cool, is he computed the Pascal's function for hyperbolic groups. And the hyperbolic groups is a really important class of groups, and remember the sort of game here is we have hyperbolic groups, we have virtually free groups as a subclass, and then we have plane groups as a subclass of the virtually free groups. So Shapiro is able to come up with a way to express Pascal's function for hyperbolic groups. And the key idea was that within a hyperbolic group, whatever inverse closed generating set you pick, the language of all geodesic words is regular. So it's recognized by a finite state automaton. So what he was doing was starting to count ways to spell the same group element within the finite state automaton. So these matrices, M1 through MK, you see here, are related to the transitions in the finite state automaton that recognizes recognizes when two words represent the same element, and so on. Anyway, it's really neat, and it's very easy to read. And so that was a cool result. And it tells us something about Pascal's function. It tells us something that's sort of interesting, and it goes beyond just seeing trees and noticing their unique geodesics. This is something about the structure of hyperbolic groups. But then Shapiro went on to pose a stubborn question. So we've seen already that if I give you a plane group, you've got this sense that you can take the finite pieces, make geodetic Cayley graphs for those finite pieces. Take your infinite cyclic factors, just put a generator and its inverse for each one of those. And you just put these together and you will construct a generating set that gives you a Cayley graph which is geodetic for a plane group. So unique geodesics. So Shapiro asked, are these the only groups for which we can find Cayley graphs where Pascal's function is identical to 1? So he pointed out that it was clear you could do it for the plane groups, but are these the only groups we can do it for? So that's the first stubborn question. Why is it a stubborn question? Because it was posed in 1997, and here we are in 2021, and we don't have an answer to the question. And it's not because people don't want to know the answer to the question. It's just it's stubborn. It's hard to get into it. Yeah. So, sorry. Peter McNamara has asked the question about whether the eigenvalues of these matrices can be greater than 1. I would have to think about that. I'll take that question on notice, and Peter, I'll send you an email when I have a look at Mike's paper. Yeah. Sorry, I don't have the answer on the top of my head. Okay. So Shapiro's question is the first stubborn question, and it's sort of this beautiful question. I like unique geodesics between vertices because that tells me I've got unique shortest normal forms for my group elements. Which groups can I get that for? Now we've got another stubborn question. An undirected graph is geodetic. I've used that word a few times before. If each pair of vertices is joined by a unique shortest path. So Shapiro's question is therefore, are the plane groups the only groups admitting locally finite undirected Cayley graphs that are geodetic? You have to throw in locally finite because otherwise you could take your infinite group and just declare every non-trivial element to be a generator, and you've got yourself a not locally finite but geodetic graph. So we're only interested in the locally finite ones. And so we're asking which groups admit Cayley graphs that are geodetic. And it turns out we've stumbled into a stubborn question in graph theory. a maximal two connected subgraph is called a block, and a block is geodetic if and only if a graph is geodetic if and only if its blocks are geodetic. And in 1967, two connected means no cut vertices, but if you take out, two connected means no cut vertices. Yeah. Yeah, connected and no cut vertices. Yep. Thanks, Murray. Yep. So the question was, what does two connected mean? And so what this means is if you want to know if your graph is geodetic, you just have to ask about the blocks. Because if there's only one vertex to get between two places, I think that one's pretty clear when you think about it. But in 1967, Ore wrote a textbook where he posed the following problem, perhaps hoping that this would give some people something to do for the next couple of years and sort it out. The problem was classifying all finite geodetic block graphs, and that has not gone that well. Just, it's a stubborn question. It turns out to be really hard. So there's just not a lot written about it since 1967. And of course, think about how cool geodetic graphs are. How often we model things with graphs and we say, wouldn't it be awesome if in our model there were unique best ways to get between things? That sounds like something we'd like to know, but it turns out it's really hard to classify all finite geodetic block graphs. So we've got another stubborn question. And Shapiro's question stumbles into this one because Pascal's function being identically 1 turns out to be telling you that you've got a geodetic Cayley graph.
It's very stupid. On the previous, so in the original stubborn question, doesn't this imply something silly about the presentation of G?
So the question is, does this imply something silly or profound about the presentation of G? Well, presentations tell you when things are equal, and you can present a group. So what's important for constructing the Cayley graph is the generating set you've picked, and then there will be things you can say about certain presentations. And I suspect, Geordie, I know what it is you're thinking of, and I'll be happy to talk to you afterwards about the consequence here. It might come up in what we're doing here, but there is a presentation going. If your generating set gives you a geodetic Cayley graph, then there is a certain presentation which is a really good choice for your group. Now, you can write relations that give you the same group with that generating set, but there's a sensible choice. Yes, it's so. The title of the talk was Stubborn Conjectures, but Shapiro posed this as a question, and I would say by now, I'm going to call it a conjecture. I don't know if I get to call things conjectures, if you know what I mean, but yeah, there's the strong suspicion. Yeah, that's right. That's right. Yeah. Yeah. Right. Yeah. So Murray's just pointed out that, lurking in Shapiro's question here is he didn't say finitely presented, he said finitely generated. And so weird stuff, bad stuff can happen, in finitely presented groups. So, but if we were to throw in finitely presented as well, or some other, my suspicion is the answer is yes, let's put it that way. And I think Mike posed the question because he thought it was yes, but he didn't call it a conjecture. So I want to get at another stubborn question now, and it's sort of coming at something from a different angle, which is rewriting systems. So I thought I'd introduce rewriting systems with an example. So rewriting systems are the ways we often work in with algebraic objects. We come up with a generating set, and then we come up with a few equalities that we use to simplify products of generators when we see them. And we hope that the few equalities that we know lead us to some algorithmic method by which we can take products of generators and put them into some form we prefer to work with them in. So here's an example here where our alphabet has 1, 2, 3, 4, 5, 7 letters, right? And they're labeled in a way that I hope is helpful. And we have rewriting rules. And so what a rewriting rule is it gives you an allowable substitution. And here lambda represents the empty word. So this first rewriting rule says if you see lowercase a followed by an uppercase a, you may replace that by the empty word. In other words, you can just omit that. And if you see lowercase a cubed, for example, you may replace it by uppercase a squared. And if you stare at just the a's and the rules for the a's, you might see here that they're defining for us a group of order 5, a cyclic group of order 5, generated by lowercase a, and uppercase a is its inverse. So that third rewriting rule there is just saying that lowercase a cubed is really the same as a to the minus 2. All right, and then we've got a different sort of rewriting, collection of rewriting rules here with B1, B2, and B3. This is working with a group of order 4, and I've identified all the non-trivial elements in the group of order 4, and then I've just written down the multiplication rules. When you see B1 followed by B3, that's equal to B2. So why don't you make that replacement? That's the way we like to work with finite groups, right? If you have a name for each element, then you've just got the multiplication table. So I've basically put the multiplication table for a finite group there, except you don't have to put in the rows and columns for the empty word, for the identity. And then the x's, well, that's an infinite cyclic group. We've got 2 generators, they're inverses of each other, and that's it. So what I've written here is the sort of rewriting rules that will give you a group isomorphic to a free product of a cyclic group of order 5, Z2 cross Z2, and then the infinite cyclic group. So this is familiar to us all for how we actually work with lots of algebraic objects. So a rewriting system isn't, by the way, there's no surprise there, that's a plane group. I wanted to show you how could I construct a rewriting system that's somehow nice, and what's a systematic way to do it for plane groups. Just take your rewriting systems for the different finite components with disjoint generating sets, write them down, and you get your infinite cyclic components in like I've done with the x's here. So a rewriting system is an ordered pair comprising a non-empty alphabet and a set of rewriting rules. Rewriting rules specify allowable substitutions. And the language we use is each application of rewriting rule reduces the word, which wouldn't be a great use of language if it's making the word more complicated in some way, like replacing A by B, C, D or something. But nevertheless, that's common terminology. And then each rewriting system determines a monoid, and sometimes your monoid is a group. When is it a group? Well, if you can check that each generator has a right inverse, then you're going to have a group. So we need to check. All right, so we can define groups with rewriting systems. And then there's some nice properties we like some rewriting systems to have. We like the generating set and the rules to be finite. Sometimes we want the generating set to be inverse closed. If the generating set's inverse closed, we know that the rewriting system presents a group. We don't have to think too hard about that. And then, but if the rewriting rules are length reducing, like we saw in that example, then one of the things we know is you can't start with a word and get stuck in some infinite sequence of rewriting and rewriting and rewriting, because you're always reducing the lengths of words. So eventually you're going to run out of letters if you don't stop. So we like length reducing, and then we also like convergent. So your rewriting system is convergent. If there's only one reduced word, that's a word to which you can't apply any more rules in each equivalence class of words. And every rewriting system terminates after a finite number of steps. So if you're in that situation, your life is glorious because you can start with any word and you just apply rewriting rules, whichever one you can see applies, you don't have to worry, and you'll get to the unique reduced word that's equivalent to the word you started with. And so it's a really happy situation, right? Finite, that would be a finite convergent length reducing inverse closed rewriting system. We like those. So here's a connection. Suppose that you have a group that's presented by a finite convergent length reducing rewriting system. Then the directed Cayley graph is geodetic. What? Well, those reduced words have to be the shortest amongst the equivalence class because you get from other words to the reduced words by applying length reducing rules. So no matter which word we start with, we rewrite it until we get to the unique geodesic that represents that group element. And since paths in the Cayley graph correspond to words in the generators which spell group elements, the directed Cayley graphs we get from groups presented in this way are going to be geodetic. And then there's a program, so this is a really nice connection. So there's a program of research started in the 1980s that aim to characterize algebraically the groups presented by finite length reducing rewriting systems, satisfying various convergence properties, weaker properties than that. Because we say, oh, this is nice. We like to work with groups this way. Computers are good at applying rewriting rules. So what kind of groups can we work with this way? So here are a couple of sort of results that are worth knowing. So the first one's a very famous result by Gromov. A group is hyperbolic. Remember, that's thin triangles, and there's lots of important consequences of that. If and only if you can present your group with a finite inverse closed length reducing rewriting system that is convergence on the equivalence class of words representing the identity. This is also known as a Dane's algorithm. Right? If you have a word that represents the identity, you can apply these length reducing rules and you'll eventually show that your word is equivalent to the empty word. So that characterizes being hyperbolic. So now we see that actually if hyperbolic groups are a really important class of groups, that's picked up by the behavior of rewriting systems. And then in 2007, so this is 20 years later, we've got the next piece of the puzzle from Gilman, Hermler, Holt, and Rees that a group's virtually free if you can apply a finite inverse closed length reducing rewriting system so that all the reduced words are geodesic. No matter which word you start with, it will be reduced to a geodesic word. It's just that there might be geodesic words, more than one geodesic for each group element, and you can't show that they are equal using length reducing rules. Right, so we see these two. I said I was interested in three classes of groups, in particular hyperbolic, virtually free, and plane. And here we see the sort of convergence properties of finite inverse closed length reducing rewriting systems, picking up the difference between those groups. And of course, maybe you'll see in the situation with the virtually free groups, there's a unique geodesic word representing the identity. It's the empty word, so that Gilman, Hermler, Holt, and Rees are really asking something more, and so they're getting something less. They're asking for something more from the rewriting system, which means you get a smaller class of groups. All right, so here are some more stubborn conjectures. We've already talked about this construction that shows that for every plane group, you can get a finite convergent length reducing rewriting system in which the right-hand side of every rule has length at most 1. You take your multiplication tables for your finite components and just write those down. And then for the infinite cyclic components, you take a generator x1 and its inverse, x1 inverse. You do that for each of those. Just put all those rewriting systems in one place with disjoint generating sets, and you've got yourself a finite convergent length reducing rewriting system. And all the right-hand sides of your rule are either the empty word or a single letter. So in 1984, Bob Gilman conjectured that the plane groups are exactly the groups presented by finite convergent length reducing rewriting systems in which the right-hand side of every rule has length at most 1. And then in by 1986, I think people were thinking this at the time Gilman made his conjecture, but the first time I could find it written down as what looks like a conjecture, said actually I think the plane groups are exactly the groups presented by finite convergent length reducing rewriting systems. So the key word here is the word convergent. We've gone from convergent on the identity, which was the hyperbolic groups, to always giving us geodesics, which was the virtually free groups, to convergent everywhere. And the conjecture is that that gives us plane groups. So in 1986, a special case of Gilman's conjecture was proved. But what's special about the case is that it insisted on the inverse closed generating set. Gilman's conjecture wasn't posed with that restriction, so it was. Remember, Gilman's conjecture is the one where the right-hand sides have length 1. So we've worked hard to set this up. So I just summarise the story so far. Theoretical computer scientists, so the sort of people working on Gilman's conjecture and so on, would like to complete the algebraic characterization of groups presented by finite length reducing rewriting systems. That's been lurking since the 80s when they were making progress on that. Mike Shapiro asked a question about groups that emit geodetic Cayley graphs. That seems like a question that geometric group theorists should want to answer. And the two of these are connected through the concept of geodetic graphs, and that links it to Oystein-Orr's question, and that's something graph theorists want to answer. And these questions have been around for a long time. Orr's question since the 60s, Shapiro's question since 97, and this program of characterizing groups presented by finite length reducing rewriting systems since the 80s. So that's what makes them stubborn. And they're connected, but they're all just, people pose questions and you say, oh, actually, I'm going to move on and do something else because we're not getting so far. So Murray and I are going to have a crack at these, which is why we're meeting here at SMRI. But I'll tell you about the progress that has been made. So some recent progress. Andy Eisenberg, who's at Temple University, and I proved Gilman's conjecture in its full generality in 2019. So we can now say if you've got a finite convergent length reducing rewriting system and the right-hand side of every rule has length at most 1, the group is plane. The group presents plane. And the key observation, if you're interested, and I've put this key observation here because you can see why the proof, whatever proof we came up with, doesn't immediately transfer and just apply to the whole algebraic program. And that is because if you're in this situation with a finite convergent length reducing rewriting system where the right-hand side of every rule has length at most 1, that has the effect that every directed path between two vertices visits every vertex in the unique geodesic between those vertices. What's going on here? Think about an application of one rewriting rule. You have a path and it's not the geodesic, and that's spelled by some word. And since your word's not geodesic, you can apply a rewriting rule. But the rewriting rules have right-hand sides. They take a subword and replace it by a single letter or the empty word. That means it's putting an edge between two vertices that were already in your path. Or it's acknowledging that you're visiting the same vertex twice and it's taking out a loop. So either way, we see that you get from whatever path you start with to your geodesic without adding vertices, new vertices that weren't visited in the original path. So every path between A and B has to visit every vertex in the geodesic from A to B. That's a really powerful restriction on the geometry of a Cayley graph. And that's not true if you have length reducing rules where the right-hand sides are longer than 1. Now, if you replace a word of length 3 by a word of length 2, you can visit a new vertex. And so that's something different. And then Murray and I proved another special case where we took our first steps away from right-hand sides of length at most 1 and said, well, what about right-hand sides of length at most 2, which turns out give us left-hand sides of length at most 3. It's enough to think about this, and we can prove that any group you present this way has to be plane. And we wrote the following at the end of our proof. Our proof offers insight into the difficulties to be overcome by any argument that takes a primarily graph theoretic approach. The point being, we did this, but it was a graph theory argument, and it didn't use group theory. And we don't think our proof for this, it was sort of performing due diligence. We're saying, can a graph theory approach really work? Could we take sort of Orr's problem and make that work? And we think it's too hard. That's it. That's all I wanted to say. I wanted to tell you about stubborn conjectures. And we've made a bit of progress. Andy and I got somewhere, and Murray and I are starting out on this. But these questions have been around for a while, and I think they're interesting they arise naturally, and they're really powerful and interesting, but they're stubborn, so we'll give it a go. Yeah, so Anthony's asking is, this is there's something strange about geodetic, asking for geodetic Cayley graphs, because it depends on the generating set. And messing with the generating set really messes with the number of geodesics. So I don't know of an obvious quasi-isometry invariant related to the number of geodesics, and I think Murray's going to cover sort of geodesic growth in groups, and so maybe your answer to that, Murray will give a better answer to that. But yeah, this is not classic geometric group theory, because it's not, the Pascal's function is not a quasi-isometry. You can really mess with it by adding new generators. But what it's really about is the best case scenario of normal forms, and how powerful a restriction it is to ask for unique geodesics. So it's something else. It's a little bit to the side of classic notions of geometric group theory. I know some people define geometric group theory as the study of stuff up to quasi-isometry, study of groups up to quasi-isometry. But I think, yeah, this is a little different. But it's got this connection to theoretical computer science and yeah. But you know, it's a really good point that it is, and particularly if you want to insist that you use a monoid generating set and you don't necessarily have inverses, it's definitely moving away from classical sort of the most usual ways to think about groups when you're using geometric group theory. Yeah. Oh yeah, if we're not planning on using graph theory, what else might we use? Well, I think the point is we are going to use graph theory, but it's got to be graph theory that's informed by the fact that this is a Cayley graph. So when Murray and I proved that sort of incremental result we proved, the key step was about geodetic blocks. It wasn't about Cayley graphs. So the fact that, for example, we didn't use the fact that the group that we know the group is virtually free, or anything about what we know about virtually free groups. It was just when you have a finite convergent length reducing rewriting system with rules of this sort, that means we have geodetic blocks with embedded circuits of length at most this, and that's what we used. So we're going to need to use the fact that the graphs are Cayley graphs of groups, and use what we know about virtually free groups. Yeah, and that was important in proving Gilman's conjecture with Andy Eisenberg. We had to figure out how to connect the geometric consequence of every path between two vertices visits every vertex along the geodesic. How to connect that to the structure of finite subgroups and the way they interact. So we're looking for that connection again. Yeah. Murray will have it by Friday. Yeah. Murray suggested Bass-Serre theory is part of it. Yeah, it's what we know about virtually free groups is what we use, and plane groups and so on. Yeah. Yeah. So the question that Anthony has is, in this theorem on the slide, when we're proving 3 implies 1, do we end up showing that the rewriting system was one of the obvious ones for plane groups? And the answer is no, we don't really, that doesn't really pop out of the proof. But you've actually touched on why these conjectures are stubborn. One of the key reasons these conjectures are stubborn is a paucity of examples of finite convergence length reducing rewriting systems, other than the obvious ones we can think of. So it's really hard to construct weird examples that challenge your expectations in a way that might lead you to constructing a group that's not plane. So our proof does not give us, does not tell us that that they're the only finite convergent length reducing rewriting systems. And in fact, you've hit upon one of the things that makes these questions hard is cooking up examples is hard. There's really only a couple of examples and in the literature, other than the obvious, than the construction I've described to. So you can mess with your finite factors only if they're cyclic, you've got a few choices. Otherwise, there's not that many options in terms of the examples that we have. But we can't rule out crazy ways to do things. Yeah. So one of the things, that's one of the things Murray and I are working on right now is thinking about how we can investigate and get better examples.
Thanks very much.
Thanks.
Hi, everyone. Yeah, I can see my beautiful building from this window, but it's very nice to be up here at SMRI. Got it right. And yeah, it's a great opportunity to be here. So thanks, everyone. So I'm going to ask this question: which groups have polynomial geodesic growth? So in order to start, I have to tell you what geodesic growth means. Okay. Well, there's my office, and that's SMRI. And this is what Google tells me is the shortest path to ride my bike. Maybe it doesn't want me to get killed on Broadway. So several options. And so the game is to figure out, here's another option here. So, and I think the shortest path according to Google is to take your life in your hands and go straight down Broadway. So, so I'm interested in geodesics. What's the shortest way to get around? Okay, so let me just have some preliminaries. So a group is generated by a subset. So I'm not interested in whether I have necessarily monoids and inverses and things. I'll just say if every element is equal to a product from S or S inverse, I can throw that in as well. So here's some examples that we're going to work with. So the group of integers with addition generated by adding and subtracting 1. But I don't have to do that. I could add and subtract 2 and 3 or any relatively prime numbers and get every possible integer. So the Cayley graph that Adam was drawing will look just like the number line if it's generated by 1 and minus 1. But here it'll look a bit different. Oh, very messy. It'll look from far away, still like a straight line, but because I've messed with the generating set, I've got different ways to travel around the same group. Okay, if I choose to use 2 and 3 and their inverses. My third example is a set of all matrices with x, y, z belong to the integers. And this is generated by just 2 matrices and their inverses. And I can multiply those together and get every possible upper triangular matrix with 1 stellar diagonal like that. Okay, so they're my 2 examples, I guess, different generating set. And if the generating set is finite, we say that the group is finitely generated by F. So that's the world that I'm living in. So let G be a group with a possibly finite or infinite generating set, and define the length of a group element, absolute value, G, to be the length of the shortest possible product of letters that equals G. So out of all the possible ways to represent G with that generating set, give me a shortest way to do it. So good, I said A, shortest way to do it. So if I'm generating, here's quiz number 1. Generating the integers by 2 and 3, what's the length of the number 10? Anyone? It's the same. So you could do 3 plus 3 for previous, yeah, previous. Oh, I need to update my number then to make it 100 next time. All right. So I think that's the best way, but there are many, you have to go through all the possibilities. So that was an easy, oh, by now, Anthony, you might be able to answer the next question then. That if we look at the set of matrices, and I just slap down a matrix, what's the shortest, what's a shortest possible way, or slightly different question, just tell me the length. So they're different questions actually in terms of computing. Given this matrix, what's the length? Well, it's going to take quite a long time to figure that out without knowing something extra clever. So this, I could put that on my linear algebra exam perhaps and just say that's it, that's the only question. And you can use Mathematica if you want, I guess. So I'm not going to answer this question yet, but that's what we need to do if we want to calculate lengths. Okay, so a word over the generators and the inverses is called a geodesic for a group element if the word computes to the group element and the length in terms of the number of letters is realizing the shortest possible way to write G. So that's what a geodesic is going to be. So here's Z times Z generated by A and B. And is this a geodesic? Is that the shortest possible way to write it? Well, A and B commute. So I can do A, B, A inverse, B, A. So the answer is no, it's not a geodesic because that cancels. And I can continue. And so A geodesic for, and this is the kind of rewriting that's not length reducing. So this group is not hyperbolic because I'm not giving you a Dane algorithm to and it's not virtually free because I'm not giving a rewriting system to push you all the way down to the identity. Anyway, the answer is no, that's not geodesic. So let's move it up a notch. So this is the definition of growth. So little gamma is a function which takes an integer and sends it to the number of group elements that, so maybe the gamma should have a little subscript of S or something like that because it's going to change. The number of group elements that have some way of writing them of length less than or equal to n. And so that's a function that you could compute if you had enough time and you could solve word problems and things like that. You could actually calculate this for a group that we give you. And that's called the growth function of G with respect to S. It's been mentioned a bit already that this is actually a quasi-isometry invariant of the group. You have to define an equivalence of functions. So exponential functions are all equivalent and different polynomial functions of each degree are equivalent with each other. And then you get a quasi-isometry invariant. So that's a growth function. And now I have another function, capital gamma, which I call the geodesic growth function. It counts something slightly different. It's the number of words over the generators so that the word has length at most n and the word is a geodesic. So we're counting all the possible geodesics that are out there. It's a bit different from, well, you can see the Pascal's function that Adam was talking about. That was counting the number of different geodesics for a single element. So if you added them all up for all elements of length at most n, you'd get a connection there. Okay, so that's called the geodesic growth function. And I think we already have alluded to this, that this is actually will depend on the generating set. So let me give you an example. Z times a group of order 2, so I'll call it C2. So I could take Z generated by A, and C2 can be generated by T. And they just commute. So I get a ladder thing like that. And the number of geodesics, I think Adam had this example. Well, starting here, I have to make a choice of where I want to go up. Nobody can see that on Zoom. No, you might if you saw the camera. So there's polynomially many geodesics in that case. However, I could mess with the generating set and I could add some other so that's called AT is equal to some new letter, I'll call it B. B equals AT, and then I'll add, do I need to add another one, or that's, yeah, I'll do C equals, oh, that's AT as well, isn't it? AT is B and AT is B, so I don't need a C. So we can, I hope I got that right, I'm just making it up on the fly, that we can get exponentially many geodesics now because you've got all these ways of choosing to go up and down as you travel along. And an even stupider way to get exponentially many geodesics is, and it's my preferred way, is to introduce another letter called A bar, and my relation is A bar equals A. So you can choose whether you choose A or A bar, they're exactly the same group element, and you'll get exponentially many geodesics. So it's, in some sense, you know, might turn your nose up at the idea of geodesic growth because you can easily just mess with it, so you can get exponential all the time. But let me try and convince you that it's kind of cool. So this is Z times Z with the AB generating set, standard generating set, and that's a reminder of the two definitions. I think, is there anything in chat? Maybe I can look. No, just still welcome back. Yeah, so the number of, I'm doing the ordinary growth, so there's only one element, the identity, and so I'll go through this fairly quickly. Some nice pictures, and we get a polynomial function for the number of different group elements in that diamond shape as you get bigger and bigger and bigger. So that's the little gamma, is the number of group elements you can express going distance at most n. However, the geodesic growth function, we're going to, you know, say this point here, you could go up or across or like that. So it's like my Google map that I had at the beginning. And so here I get an exponential function for the number of geodesics. I think that's not a surprise. So that's just for some particular choice of generating set. But what I'm going to have on a slide in a few minutes' time is that it doesn't matter which generating set you choose for Z squared, it's always exponential. So there's a nice geometric argument to say why that's true. So anything with Z squared, and then, yeah, so you'll see. So at the moment, I'm just doing explicit examples, but we want to have statements that say, well, the geodesic growth function, we know we can always make it exponential if you want to do something stupid, but what's interesting is when the geodesic growth function is always exponential, that sort of thing. And then the question of the title of the talk is, which groups is it possible to find a generating set for which the geodesic growth is polynomial? So that's the example, it's still going on. Oh, that's just that little path. Okay, so I want to talk about types of geodesic or normal or ordinary usual growth functions. So a growth function can be exponential if it's bounded below by an exponential. I guess the previous slide, you know, it's not always the perfect exponential function. It's always going to have some noise in it. So we have these definitions of exponential if you're bounded below by an exponential function, polynomial if you're bounded above by a polynomial, and you know, may not exactly have n to the d for some particular value. It could bounce around, some interesting things happen. And intermediate, if it's neither exponential or polynomial and it's somewhere in between. And why don't I consider anything else like factorial or something? Because this is the number of group elements that can have at least one thing representing it. Well, that's obviously smaller than all the possible ways that I could write geodesics. Adam was interested in when these two functions were actually equal, when there was only one way to write things. But in general, we're expecting this to be bigger. And then this is just the number of words of length at most n satisfying something. So that's bounded above by just the number of words. So exponential is as good as as big as you'll ever get. So that's why this is the interesting thing. And we define an equivalence for usual growth. I won't write it down here, to show that two polynomials of the same degree are equivalent, and a constant function is equivalent to a linear function, things like that. Purely for the purpose of making the usual growth function a quasi-isometry invariant. You change the group a little bit and it should stay you want to prove that it's quasi-isometry invariant within these things. Okay, so what are the major results in geometric group theory, in my opinion, my humble opinion? So Gromov proved that a finitely generated group has polynomial usual growth, the little gamma, if and only if it's this algebraic characterization, virtually nilpotent. So I'll say what that means in a second. So something just totally about geometry is totally equivalent to having an algebraic structure like this. So I'll come back in a minute and say precisely what virtually nilpotent means. But for now, you can just think it's some strict algebraic property. Milner, long before this, asked, are all group growth functions gamma polynomial or exponential? Is it possible to have anything in between? And because Milner couldn't think of anything. And Grigorchuk constructed an explicit example of a group acting on rooted binary trees. It's a beautiful example that actually realizes this intermediate growth. We still don't know the precise function, but it's somewhere in between e to the root n and e to the some number, and they get closer and closer all the time when people work on it. So it's sort of fascinating that this exists, and once this appeared, people started producing other examples of things with intermediate growth. So I would say that, if I'm very biased, I think, but that these two results about growth, about usual growth, are pretty big ticket items. And so I'll say my big questions: does there exist a group with a finite generating set so that the geodesic growth function is intermediate? So we have that inequality that the usual growth function is always less than or equal to this geodesic growth function, which is bounded above by the exponential there. So the usual growth function, in order to answer question one, what am I going to be looking for? Something where the usual growth function is either polynomial, and then you only add a little bit more stuff, not too much more stuff, or you take a group that has intermediate geodesic growth to begin with, and you somehow don't add too much stuff when you, would be ideal if it had unique geodesics. I mean, that would answer everything that we want, but I think that's pretty unlikely. So you take maybe an intermediate growth group and you find one where maybe you just have bounded number of geodesics for each group element. So Pascal function could be bounded. Or it would be good enough if Pascal function was polynomial or Pascal function was intermediate. Because you've got intermediate number of group elements multiplied by not too many representatives for each group element. So I think this is a beautiful, beautiful question. and I don't know how to answer it, but I want to. And of course, it depends on, you know, maybe I can mess with the generating set too, to just so it happens. So I think that's a great question, but I won't dwell on this one too much. I have things to say about it, but not too much. A student of Lara Chubano, when she was at Neuchâtel, and I was visiting and I got her hooked on this question, went through a paper of Bartholdi where every group of intermediate growth was kind of listed, and she checked every single one of those, and with the standard generating set, they all had exponential geodesic growth, except for one, which we didn't know how to do. Anyway, cool stuff, but I'll go to the second question, which is characterize the groups which have polynomial geodesic growth with respect to some finite symmetric generating set. So this is the Gromov question. Can you prove a Gromov theorem? And this is like the Grigorchuk or Milner question. So the theorem that we would want here is that a group has polynomial geodesic growth with respect, you know, it's possible to have some generating set for which it has polynomial geodesic growth, if and only if it's fill in the blank. So virtually cyclic, because we already had that example. That's a virtually cyclic group that I can get polynomial. Anything else? And the maximum it could possibly be, because of this lower bound, if you want that to be polynomial, this has to be polynomial as well. So we're only looking in the virtually nilpotent. But is it all of them? Like, is all of them, or is it only the virtually cyclic? That's the only one, when I started looking at this, is the only thing I could think of to do. Okay, so I think they're my big questions. This is the definition of nilpotent from Wikipedia, if you like. So nilpotent of step C, if this lower central series where you start with a group and then you take a new group, which is the commutators here, and then you iterate that process and it terminates after a finite number of steps. So if a group does this, so obviously an abelian group would stop very quickly, and the group of matrices, I only really have 2 examples in this whole talk, also satisfies this. So this was also on my linear algebra exam, but it could conceivably be there. Okay, so this is just my go-to example of a nilpotent group, and it terminates after 2 steps. So and abelian will terminate after 1 step. So it's kind of the easiest step away from just being an abelian group that you can have. Okay, and it's called the discrete Heisenberg group. Virtually, let me put all this up. Virtually blank, and you can fill in the blank with any group property that you like. So virtually trivial, if you like to do that. A group is virtually something, means that G has a something subgroup of finite index. So a finite group has a trivial group as a finite index. That's why we always make that stupid joke. Now I want to just say informally, that means that you can think of your group as a finite number of copies of another group K, which has the property that you really like. So Adam was talking about virtually free. He gave some weird definition of it. But virtually free means you've essentially got a free group with just a little bit of finite stuff, a few finite copies of a free group. And the way it's glued together is maybe a little bit complicated, but that's how I think about them, because I'm a bit basic here. For example, I'll just take a direct product. That's a pretty easy way to glue 2 copies of some group together. So H is the Heisenberg group from the previous slide, the set of matrices. And if I just take a group of order 2, I have 2 copies of Heisenberg group, whatever it looks like, and I just go between them with this letter that I was using before, like T. So that would be an example of virtually nilpotent. All right. So here's the theorem again of Gromov. A finitely generated group has polynomial geodesic normal growth, regular, usual growth, if and only if it's virtually nilpotent. Okay, so we're thinking of some kind of copies of Heisenberg group glued together, finitely many copies. So that's it. It was known before, I think it's Bass, right? That if you have a virtually, virtual doesn't change the usual growth function. So it's a to take a finite index subgroup, the growth function doesn't change. So I think Bass already calculated for any nilpotent group of step C, it has polynomial growth function related to C, probably C plus 1 or something like that. Oh, the ranks of the quotient. Okay, yeah. So we already knew that, Gromov already knew that virtually nilpotent groups did have polynomial growth of integer degree. And so what Gromov proved was that that's it. There's nothing else. It's a super hard proof, but Terry Tao put a new proof out a few years ago, and there's been a few different attempts. And I'm just repeating everything. So this is this crucial observation here. And I said this already. The only candidates that we could be looking for polynomial and geodesic growth are the virtually nilpotent ones anyway. Okay. So here's Shapiro again, Mike Shapiro. Z squared has exponential geodesic growth with respect to every generating set. Just quite a simple geometric argument for that. No matter which generating set you choose, you'll always have choices of how you're traveling around in that generating set. So you'll end up with an exponential. And so in 2012, a bunch of us tried to say as much as we could about polynomial geodesic growth. So the paper is called On Groups, whose geodesic growth is polynomial, but we couldn't really say much. That's what's going on groups. So G finitely generated strictly nilpotent group, so not virtually, just a proper nilpotent group. We essentially proved that you could push a Z squared inside it, and in such a way that the Z squared has exponential growth, and so that it's a little complicated, so maybe I shouldn't, and I can't remember the proof anymore. So long ago. So if G is not virtually cyclic, because that's possible for nilpotent, then G has exponential growth with respect to every generating set. So that rules out all strict nilpotent groups. Yeah, so my vague recollection of the proof is you just push a Z squared inside the group. Okay, but at the same time, there was this example. It's actually due to Jim Cannon. He was trying to prove something else. And it's virtually abelian. It's two copies of Z squared stuck together. That's the way I said I'm going to vaguely think about it. So I've got A and B generating a Z squared. I've got my T squared equals 1, just the easiest thing you can do. And now they're glued together with this relation TAT equals B. So let me show you some pictures. That's just a copy of Z squared. So that's B, and the red, I think, from memory, is A. So that's just Z squared, Cayley graph. Now I'm going to put another copy on top with a 90-degree twist. So I've got a bit much, but two copies of Z squared. And now finally, the T is in black. Let's have a look. So this is, red is, so I go down, T, A, T. And now for the viewers at home, T, A, T is the same as B. So that's the Cayley graph of the group. So Cannon then used this to prove something about regular languages of geodesics. That this has a regular language of geodesic, but if you mess with the presentation and put extra things like I was doing before, so C equals something and D equals something else, you end up getting a real mess. But what I did with this example a long time ago was removed. It's a huge my greatest theorem ever, was to say, oh, don't do what Cannon did and add more junk and make it terrible. Make it simpler. Delete the B. Because B you don't need. B is equal to TAT. So that was my great breakthrough here. And you end up with this Cayley graph, which has polynomial geodesic growth. Because let's say, okay, we're doing Google Maps again. I want to get from here to here. There's my office, that's SMRI. Well, I have to travel horizontally, and at a certain point I'm allowed to go up. I have to go up, because otherwise I'll just be stuck in this line, because there's no B anymore. So then I say, all right, I'm going to do it there, and I better come down at the right level, otherwise it's not going to be a geodesic. I shouldn't be jumping up and down more than twice, because that's a waste of time. So I have polynomially many geodesics that says that linear number of choices that I can make along there. So I think it's pretty simple, but it's kind of cool, because before we had this, we were thinking, well, the only thing we can think of is just take Z and do virtually Z. And so I'm like, no, you could do this with any ZD that you like. You could do this trick. Because essentially what you're doing is you're favoring one direction in a, favoring one direction, and then because you have two copies, if you want to travel in a different direction, you have to jump over into a different copy. All right. Sometimes I feel I should have done optimization instead of group theory. Yeah. Three things coming out of it. Because t squared equals 1. I've got an A coming in and an A going out, and a T, Adam might draw it directed, but then T times T. B disappeared because I deleted it. And I don't need B because B is equal to TAT. So this is called a TT transformation. So it's the same group because TAT, which is here, you could replace that by B and you get AB equals BA. Yeah. So this is something that we do. The original group is that, but we're just renaming group elements and things. It's virtually abelian. It's not strictly nilpotent. So the previous result, if I have an actual z squared, then it has to be exponential. And if I'm a on the nose nilpotent group, so this group is not nilpotent by itself, it's virtually abelian. Yeah, so it's not strictly nilpotent. So it has to go infinitely along. That's a good question. I need to, yeah, what's the commutator subgroup of this? This is my PhD student, Alex Bishop. And this is the most awesome result in the talk here. My results are like, here's an example, and I remove the B. That's like my contribution to the world. So what I gave Alex as a little warm-up for his PhD was say, all right, we know about nilpotent, and really I want to go after virtually nilpotent and prove Gromov's theorem. So I said, PhD student, you have to prove Gromov's theorem. That's your task. And I said, as a warm-up, do virtually abelian, because how hard can that be? Well, it turned out to be pretty full-on. And Alex was able to prove that for any virtually abelian group, the geodesic growth is either polynomial or exponential for any generating set. And the proof is really surprising that what he did was get a bijection between the set of all geodesics and a kind of formal language that the paper is fascinating to see how this sort of crops up. The formal language called linearly constrained, which is the intersection of a context-free language with some restrictions called linear constraints. So it's sort of an, you might say, obscure language class. And then Masaza proved that the generating function, counting the number of words in such a language, has to be what's called D-finite. So we're off into numerical combinatorics world, or analytic combinatorics. And D-finite functions can't have intermediate growth. So it's a really roundabout way to prove it. So, because going directly, weird things can happen in abelian groups. So that's a cool result, and it's involved. So here's another result. It's not as cool. It's from 2012. So it's before Alex had figured everything out with abelian groups, virtually abelian groups. This is what we think was going on. If you want to get polynomial geodesic growth, it's not an if and only if statement, so it's pretty weak. But if you can find a single group element whose normal closure is abelian and of finite index, and so suddenly the group is virtually abelian, then you can rig together a generating set, making this group element the dominant one, essentially. So this theorem is basically taking my little baby example and turning it into sort of a fancy theorem. So if you can somehow rig that up, you're already going to be a virtually abelian group. So this isn't really producing anything else. Then you can get geodesic growth, which is polynomial. And there may be other ways to do it, but I don't know how to do it any other way. Well, I do now because there's a theorem coming up. But at this point, I didn't know how to do it any other way. So that's one way to get polynomial geodesic growth. But is there any other way to do it? Is that all there is? So for example, can you get a virtually nilpotent group of every class or step? You know, that then we'd have the analog of Gromov's theorem. Another thing that I really like to do is, because Gromov's theorem turns out that every the polynomial growth function that you get for usual growth is always an integer degree. Whereas it's conceivable you can have a funky generating set and get some kind of interesting polynomial bounds with different degrees. So, but I don't know how to do that with this construction. My only one trick, I'm the one trick pony. So let me answer this question. No, it's not all there is. And this is another recent thing that I did with Alex. Well, I tried to distract him from his big paper and said, oh, let's play this game. So I wanted to just copy my one trick. Take the Heisenberg group, and that's the presentation for it. Same matrices that I had at the beginning. And I want to glue them together and delete the B. I'm pretty naive. I just want to do exactly the same thing as before. So let me draw some presentations down the bottom. So I'm adding a t squared. I'm really not a very creative person. And I'm replacing, I'm sending A in one copy of Heisenberg group turns into B in another copy of Heisenberg group. So let me draw a schematic. So here's one copy of Heisenberg. Here's another copy of Heisenberg. T was black before. So the T, you know, if I want to, I'm reading A's in one copy of Heisenberg group. Now I want to read B's. Well, if I'm going to delete the B in each copy, I'm going to have to travel over to the other copy. Then I can move in the B direction. And if I want to start reading A's again, I have to travel back. And I really don't want to be traveling backwards and forwards too many times, because that's a waste of time. I want to do as many A's as I can in one go, and then travel. I have to do B's eventually. So I do as many B's as I can in one go and travel back. So that's as far as I got. That was my, surely it's the same trick as before. Does this work? Does this give me something of polynomial geodesic growth? Well, it would be polynomial if I could prove that for every group element here, there's always a bound on how many times I have to jump backwards and forwards. So what that would mean is in an individual copy of Heisenberg group, you could somehow prove that every group element in the usual Heisenberg group, there's a geodesic that doesn't switch between A and B too many times. Yes. Yeah, T is a coset. I've got two cosets here. Yeah. Yeah. If you prefer a more accurate picture, this is one that Alex rigged up with ticks, but I don't really think this helps. to understand what's going on. So I think I'm thinking of being in one copy of Heisenberg group and traveling around A's and B's, but then I've removed the B. So I'm traveling around in A's, and then if suddenly I really want to read some B's, I have to do a T. And now I'm free to go in that B direction and come back again. So that was the idea, and it turns out, and so let's recall my question at the start. What was the length of that? It turns out that someone, French, Blacher, wrote a paper, just brute force sort of, calculating a distance function in the ordinary Heisenberg group. And so it's why would you ever want to read such a paper? It's like, this is how, given a group element of Heisenberg group in, A, B, it tells you the distance, the length of that group element. It's like a formula, and it's case by case. It's pretty, not the most exciting thing to read, but Alex actually found this paper because it was called growth, calculating the distance in Heisenberg group or something. So it has an explicit length formula with respect to this generating set. But what was hidden inside the paper is the following fact, that it's not even stated as a lemma or anything. It's just like a tool, that every element of the Heisenberg group, that explicit example, has at least one geodesic representative where you only need to switch between A's and B's at most 6, or there's only at most 6 factors here. Now, that's exactly what I said I needed. So what this proves is that every group element in the virtual Heisenberg group that I've created, the geodesic, you better choose these sort of representatives of group elements rather than an equivalent geodesic. So this result says there's other ways to write it as a geodesic. You could swap between A and B like 100 times. But now when you put it in my virtual Heisenberg group, that's not an efficient way to work because you're going to be using 100 T's. Whereas the fact that this is true means that I only need at most 6 or 7. I think we need one more just in case you need to go up and up at the very beginning. So that's the key fact. And using this fact, we get this theorem. It's not been accepted anywhere yet. So the group VH is virtually nilpotent of step 2 and has polynomial geodesic growth. I don't know exactly what the growth rate is, and I really hope that it's some number that's not exactly an integer, because that would be cool. And I can only do this theorem for that particular example of Heisenberg group because I need another French person to calculate distances and prove a theorem like that for me. So I don't know whether you could do some other Heisenberg of higher step, because we don't have that fact. So it's a fairly limited thing. Exactly, that's another. You could have A and B, and then the C is just AB, A inverse, B inverse, which will just be what you said. Yeah, but so every group element could be written as some power of A, some power of B, some power of C, because you can commute A's past B's and at the expense of creating C's. But that's not a very geodesic way to go. Because the amount of time you switch between A and B costs you C's at the end of the word. So if I had AB, 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 and I tried to push it into that form, the C would just go through the roof. So it's totally optimization of how do you express a matrix in the most efficient way. And the fact that you can do it with only these 6 swaps, I think is kind of a miracle. I don't know why that's true. And it seems, it'd be great if it were true for every possible, actually it wouldn't be great, because then the theorem will just be every nilpotent group of any class, you can find some virtually nilpotent thing that has polynomial growth. And I don't really want that to be true. What I want to be true is that the answer to the question of the title of the talk is that it's only possible for rank, for step at most 2. But yeah, why should I have think? So, okay, sorry, I'm a bit over time. Here are my questions. Is that all there is? Well, I don't know. Can I do anything better than step 2? What's the degree of the polynomial? So this is related to the intermediate growth question that I said at the start. And this is sort of how I got talking to Adam about groups with unique geodesics and stuff, because I wanted to show that the Gupta-Fabrikowski group had, or some group of intermediate growth, had a bounded number of geodesics for each group element. And so, yeah, my final thing is, what about geodesic growth, which I could tell you all about, what I don't know there, but I'll stop. So thank you. I just think that would be cool. Yeah, if, you know, the analog to Gromov theorem was weird. But, or, you know, it could be some low dimension thing. Once you have more degrees of freedom, you can suddenly stick a z squared in there and go for it. This is the way we state this theorem. And I'm like, if G is not virtually cyclic, but that's strictly nilpotent. So that's a different situation. Yeah. Anyway. Yeah, I think it would be a tricky, an awesome thing to look at, because you've got the set of all words with at most 6 or 7 T's in them and the rest A's. That's pretty easy. But they're really, this paper of Blacher gives you all these conditions that you could somehow turn into linear constraints or something maybe. So you could possibly give a description in terms of some formal language by reading really carefully Blacher's paper and his case-by-case analysis of things. Yeah, so I'd like to know that, and maybe from that we could get the actual growth bounds. So we never get it on the nose. You get an upper bound and a lower bound of 2 polynomials, and they might be between 7 and 8 or something like that. So that would be really fascinating. You know, if the actual growth rate was 7.25 or something like that. I think that would be awesome. So yeah, it's a concrete example, and there is this paper of Blacher that you can go through with the excruciating detail and decide which one's geodesic, which one's not geodesic. And it's simply just adding up the number of A's and B's and C's. So yeah, that's awesome. There's something called bounded generation, and it's about being able to express every group element of some group using a bounded number of cyclic subgroups. I should look up what bounded generation is and see whether I can get any other examples. Oh, can I indulge and show one thing that so Alex, before he started his PhD with me, did an honors project doing, doing the Fabrikowski-Gupta group, which was this one example that came out of Julie Bronneman's thesis that we don't know whether it has exponential geodesic growth. So Alex wrote a computer program to, and I found this, I thought, oh, I'll add this if I have time to the talk, which I don't have time, but I'm adding it now. So I wrote a computer program, so don't look at this side yet, to do Pascal's function, essentially. And this is the maximum value of Pascal's function for all words of length, you know, group elements with lengths 12, 13, 14. And so when we did it with other groups, like a Gorchak group and things, these numbers were growing exponentially. It's like, we're really growing. And for Fabrikowski-Gupta, they really weren't growing much. And, you know, I was super excited. He got out to 25 and I'm like, oh my God, this is going to have bounded number of geodesics. And I was like super excited. But then he did 65 and then I think I just shut the computer down. So I don't want you to do anymore. And he finished honors and we haven't really got back to that. But I think this might be a candidate maybe of being able to maybe find something of intermediate growth. I think that would be super exciting as well. Thank you. All right.